Cool. Um, well, this is our bike trick program.
Okay, so the type of data we decided to analyze was bike tricks. So there's like hundreds of different types of bike tricks, and they all have different descriptors to them. Like, for example, you have rotations and flips and ones where you're taking your hands off. So we decided to test out a couple different data structures to organize all the different types of bike tricks and see which ones were the most effective. So one function that we used to test our structures was being able to look up single specific tricks, and then another was looking up a whole category and returning all the tricks in that category. And of course, we also had an insertion and deletion into the structures.
The data structures that we have decided to implement is the hash table, which allows for quick searches of one, minimal collision, and having a unique key which prevents collisions. And then the other implementation was the array of stacks, and that allows us once again to get a whole category of tricks and implement them.
All right, so for the hash table implementation, we used the unordered map library in C++, and this made like understanding the processes behind the code a little bit interesting, because it's kind of a black box where it's like generating a hash key and inserting it into the table, but we don't know exactly how it's doing because it's more advanced than what we've learned in class as far as hash tables go. But according to the documentation, insertion and deletion and looking up a single item is an average of O1 time and a worst case of ON squared time. And the way that our implementation works is we have a text file with comma separated values for every trick. So the program reads the file, inserts the trick as a struct into the table and the key is the name of the trick, because every trick has a unique name. And then, yeah.
Then our other data structure that we implemented was the array of stacks. The way we did this was by using a vector as the array, since typical C++ arrays cannot hold stacks. So the vector would be holding each different stack, which is a category of bike trick. Then when the user inputs a category that they would like to see all the tricks for, it would go through the stack and pop each one off the top of it to to then print that trick. And theoretically, it would run in n plus m time, n being how long the vector itself is, and then m being how long the stack is. Here's our analysis.
So for the hash table, we found that we got what we expected from reading the documentation. So for example, the deletion, insertion, and searching for one element, they have kind of the sporadic looking graphs because they're running close to O1 time most of the time, but then when the algorithm is unlucky, it spikes up and approaches n squared time. And then for searching for a whole category, we get a linear graph, which makes sense because it's a for loop that iterates through the entire table and checks if each one fits in the category you're looking for. So essentially it's an average of O1 process for n elements in the table, so we get the linear graph as we increase the number of elements.
So for our array of stacks, the time complexity is a little unclear due to the fact that for bike trick specifically, the n time of how long the vector is always the same. So when we tested 100 and then 1,000 and then 10,000 items, what was reflected was closer to what would be O of n time, with it just increasing with more elements. The time taken for each run was quite inconsistent with the amount of elements that it had. Like once it increased elements, on the 10,000 item run, it would usually take around 15 seconds or so for it to actually run properly the first run, but then the next few would be in decreasing speed. That could be explained by like a multitude of things, but it probably had something to do with the program that we were using rather than the code itself.
So in conclusion, we found that the hash table was recommended because of how much easier it was to avoid collisions. The array of stacks was able to search the categories, but just took a lot longer. Maybe with more testing, we could get it shorter, but it wasn't as practical.
And that's all for the presentation. Now we just wanted to show how the code works itself. So I will pass off the screen sharing for Charles.
Cool. Okay, so this was our code to make a file of randomly generated tricks, because of course we couldn't come up with enough tricks to be able to see a dramatic difference in the runtime. So when you run this, it just builds a file with however many num items. So this is a huge file it just made with 900,000 elements. And then when I go over to my hash table implementation, you can run it. And I have it so it just runs all of our functions once and returns the time it took. So as you can see, it didn't find this item because it was not in that file of random tricks. And then if you want to delete a trick, I can look up, let's see. A random trick, and it will delete it, and it took that many fractions of a second.
Nice. Cool.
My share.
So this is the program of the array of stacks. I have it set so you can do multiple things, but it should have already implemented 10,000 tricks into there because that's what I had it set to last. So if I press 2, it should give us an option of what kind of trick we want. I have it set to put all of the 10,000 into one category, and so as you can see, these are all the air tricks, and it takes quite a while for it to run fully because it is 10,000 items. But this is what it'll do, and then once it gets to the end, whenever that'll be, it'll say how long it took to retrieve all of those items. So yeah,